By engine, I just mean a chess framework you can use to give your bot commands. You can make your own, but that requires a lot of work, so it's best to use an existing one like chess.js or Python chess. I'm going to use Sebastian Lake's framework that he made for his chess coding challenge because I used it before and it's in C#. But you can use pretty much anything that works for you. You can download it using the link in the description. After opening the project in an IDE of your choice, I'm using Visual Studio, navigate to the mybot.cs script. This is the script that you'll be writing your bot's code in. At the top, you'll see the green play button. This is to run the whole thing. If this doesn't show or work, you can open it with .NET Run in a terminal. This is explained in the FAQ section on the GitHub page. In the file mybot.cs, there's a function called think_move. For now, let's make the bot move at complete random with this code. The bot isn't exactly the greatest of players right now, so let's fix that. First, let's add an evaluation function to see which player is in a better position. This simply adds up the worth of every white piece and every black piece on the board. A positive value for white pieces and a negative value for black pieces. Better pieces are worth more value or material. Then we'll add the worth of the two sides. To start with, this will be 0 because both sides have equal pieces. Keep in mind that white wants to maximize the evaluation, so make it positive, and black wants to minimize it or make it negative. In the code, create a function called evaluate that returns an int because the evaluation is a number. It'll take in the board as a parameter. Create a variable to store the total material. Loop through all the 64 squares. If there's a piece there, add that piece's value to the material. To do this, I'm just going to multiply that value by -1 if the piece is black. At the very end, simply return material. Create a variable to keep track of what color the bot is playing as, and in the think function, set it to board.isWhite to move. Create a variable of type move to store the chosen move, and an int to store the current best evaluation. If we're playing as white, it's int.min value, and if we're playing as black, it's int.max value. This is so that before any move is chosen, the best evaluation is the worst possible move. Now create a loop that goes through every legal move on the board and evaluates the position. The way we do this is to make the move, get your evaluation, and undo the move. Keep in mind the move isn't actually done in the real game because we didn't return it. The move is just done internally in the program so the bot can check it. If the evaluation is better than the current best evaluation, update the chosen move and best evaluation. Remember, the evaluation is better for white if it's more, and better for black if it's less. Finally, return the chosen move and run. You can see the bot is playing okay, and it captures pieces when it can. But since the bot can't look more than one move deep right now, it doesn't know if 2 turns later it'll get captured. To fix this, let's add some depth to the search. The Minimax algorithm is like a tree and lets us search more than one move deep. Let's imagine that this circle is the current position on the board and it's white to move. To keep it simple, say that there are only 2 legal positions to play, represented by these branches. At the end of the 2 branches are the new positions, and then it would be black to move. Another move deep, it would be white's turn. The amount of moves we search deep is called the depth, and the higher the depth, the more moves the program has to search, and thus it would take longer. Let's limit the search to the depth of 3 to keep it fast. These last circles are like the leaves of the tree, and we'll evaluate those positions. Looking at the first 2 leaves, let's say their evaluations are -2 and +2. If you retrace the branches, you can see that in the last position, it was white's turn to move. Out of the evaluations -2 and +2, white wants to choose the one with the higher evaluation, because that's better for white. So that would be 2. The next 2 leaves get evaluated as -4 and -1, and white would choose -1. Now let's look at the move before this one. It's black to move, and out of -1 and +2, black wants to choose the one that is less, so that would be -1. Let's move on to the other side of the tree. These 2 leaves evaluate as +3 and -4, so white chooses 3. The last 2 leaves evaluate as -2 and +5. White chooses 5. Out of 3 and 5, black would choose 3. Now over here we have 2 moves for white to decide from, with the evaluations -1 and 3. The better move for white would be 3, so the bot plays this move, going down this path. Even if black plays the best moves, white can still make its most advantageous moves. Essentially, the Minimax algorithm maximizes the player's chances of winning, even in the worst positions. It can be used in tic-tac-toe, Connect 4, or any other 2-player game, not just chess. Now let's implement this in code. First take the chosen move variable out of the thing function so it can be used anywhere in the script. Create a function that returns an int called Minimax. It'll take in the void, an int for the depth of search, and a bool to know whether the player wants to maximize the evaluation or minimize it. If the depth is 0 or there are no legal moves to play, just return the evaluation of the board. Let's start by writing the code for if the player is maximizing, which would be white to move. Store the variables for the best evaluation and move found so far. Default the best evaluation to int.min value and the move to the first legal move. This part is similar to what we already have, so I'm just going to copy part of our previous code. Instead of an evaluation of the board at the current moment, replace it with a recursive call to the minimax function. Pass in the board, depth -1 and false because next move it'll be black's turn and black wants to minimize the evaluation. If the evaluation is greater than the best evaluation so far, update the variables best eval and best move. After the loop is finished, set the chosen move to the best move and return max eval. For the minimizing player or black, it's very similar, so just copy and paste the maximizing code. The difference is that black wants to minimize the eval, so default the best evaluation to int.max value. When we call the minimax function, the bool is maximizing player will now be true because in the next turn it will be white to move and white wants to maximize the eval. Over here, the evaluation would have to be less than the best evaluation for the move to be better. If you get an error saying that not all code paths return a value, just return the evaluation of the board at the very end. This will never be reached because of the if statements earlier, but it stops the error. In the think function, remove all of this code and simply run the minimax function before returning the chosen move. It'll take in the board, a depth, I'll set that as 3 for now, and the bool playing as white. If we play the same position as last time, you can see the bot doesn't capture the pawn this time. This is because it knows that the defending pawn will capture it, resulting in an unfair trade. You might realize though that increasing the depth to 4 makes the search take a few seconds. I logged the amount of moves the bot searches, and that's a lot. Let's look at the simpler tree with only a search depth of 2 and white to move. The first two leaves evaluate as -1 and 2, so black chooses -1. The next leaf evaluates as -4. Currently, the best move for black would be the branch with the -1 evaluation, but as soon as this leaf gets evaluated as -4, this branch immediately becomes a better option for black. No matter what this leaf is, the second branch is worse for white than the first branch. This means they can completely skip evaluating the last leaf or prune it from the tree, and white can safely play the first move. We save time, but the final outcome won't be affected. One thing I want to point out though is that alpha-beta pruning only happens when the best move for the player whose turn it is in that position are evaluated first. For example, if this leaf's evaluation was -2 instead, it's not better than black's move so far. We would still have to search the last leaf. If you're looking for a more in-depth explanation with a more complex tree, you can find a great video about this by Sebastian Lake. So the code for this is fairly simple. The minimax function will take in two new integers called alpha and beta. Alpha represents the best score white has found so far, and beta represents the best score black has found so far. Here, when we call the minimax function, just pass in alpha and beta. If the evaluation is better than alpha, we want alpha to be set to that. Instead of an if statement here, you can simply use the math.max function. Now, if beta is less than or equal to alpha, it means that black already had a better move before and we can stop the loop. For the minimizing player, pass in alpha and beta into the minimax function again. This time, set beta to whichever is least, the eval or beta. If beta is less than or equal to alpha, break out of the loop. When we initially call a minimax in the sync function, pass in int.min value for alpha and int.max value for beta. Okay, here's the tree from before, but now let's look at this with the alpha and beta variables. To start with, their int.min value and int.max value until the first leaf. This gets evaluated as -1, and that evaluation is less than beta, so beta gets set to -1. 2 is not less than beta, so nothing happens now. Then we tell the parent position of this node that so far the best outcome it can have is -1 by going down this branch. So alpha, or the best move for white so far, gets set to -1. Then the value of alpha is passed down to the second branch and given to this position. This leaf evaluates as -4 and that's less than beta, so beta gets set to -4. If you remember in the code, pruning happened when beta was less than or equal to alpha. Right now that's the case, so we can safely stop the search for the rest of the nodes. In this case, there's only one remaining node. Okay, the depth is 4 and the bot is responding much quicker compared to earlier. This is the amount of moves being searched and it had quite a significant drop. There is one thing that slightly bugs me though, it's this. The reason for this repetitive play is because the bot has no knowledge of pieces like knights being best in central squares. If two positions end up with the same material, the bot treats them the same. You can add a tiny bit extra to the evaluation when a knight is in a central square or any other sort of position you see fit. This is a very inefficient way of implementing this, but it works for now. Okay, I'll leave you with some very grandmaster-like play from me against the bot.